In this lesson, you're going to get a little bit of a break from calculus, and we're going to go back over some rules that you learned back in Algebra 2 and Pre-Cal about exponents and logarithms. So just bonus information up there at the top. John Napier is the guy who figured out the way to turn multiplication into addition for logarithms and division into subtraction. That made it a lot easier to calculate logarithms back in the day. But now that we have calculators, really not quite as useful, not used as much. We still learn how to separate them, though, because it's helpful for our derivatives. And so we're going to be going over those rules about multiplication becoming addition and division becoming subtraction, and also the rules for exponents. And one of the things that we're going to be looking at, or the main derivatives that we're going to be looking at, are the natural logarithm, which is base e. And so they do talk about here what the value of e is, which we have mentioned before, but we didn't ever mention where it came from because you couldn't understand because you didn't know any calculus. But the actual number e is defined by taking the limit as n approaches infinity of this equation, 1 plus 1 over n to the nth power. And we get e, or is 2.71828 on e. There's more to it than that, but those are the decimal places they gave us. So anyway, all of that just bonus information. You don't really even need that. Just extra stuff up there. So what we do need to know are our rules, our properties for exponents, and our rules or properties for logarithms. So we know that when we multiply, we add the exponents. So if you see exponents added, it was multiplication. Multiplication becomes addition of exponents. Power to a power, you multiply. So we could separate it back out as a separate exponent. Anything to the 0 power is 1. A negative exponent becomes positive when we move it down to the denominator, and division is subtraction. So those are all of our rules for exponents. And then down here, we have our rules for logarithms, which are very similar because logarithms and exponents are inverses of one another. So we know that when we have a log that is multiplied, we could separate it with addition, or if we have addition, we could put it back together as multiplication. For our derivatives, we're going to be taking them apart. Also, we know that if we have an exponent inside our logarithm, we can bring it down to the front. We know that ln of e equals 1. This one is very important for you to remember, but here's why, just in case you've forgotten. Ln is log base e. So e to what power gives you e? Well, e to the first power gives you e. You can't take the log, or the natural log of 0, and ask out here why. Well, if you try to raise e to some power, some exponent to give you 0, there is not one. There's no exponent that you could raise e, or any number to for that matter, and get 0. So you can't take the log of 0. Also, we learned when we were using our logarithm rules that division could be separated into subtraction. This one's also another very important one for us to know, but it's easy to figure out too. E to what power gives us 1? E to the 0 power. Anything to the 0 power is 1. And then this one is the same as what we had up here. When we have a negative exponent, it becomes a fraction. And so if we have a negative in front here, then remember that could be brought over here as an exponent. This is x to the negative 1 power. X to the negative 1 power is 1 over x. So these are our rules for exponents, for logarithms and exponents. So on the back, they have a place for us to review graphing the logarithm and the exponential functions, and also places for us to practice our rules. And so when we're graphing, we'll do e to the x first. If I have y equals e to the x, then I'm just going to graph a couple of points. Well, I know that when I put in 0, e to the 0 power, anything to the 0 power is 1. When I put in 1, I get e, and e is about 2.7, 2.71. So we have the point 0, 1, and 1, 2.7. So I know that this graph is going up like that. This is y equals e to the x. And so my domain and range, my domain would be all real numbers. My range would be from 0 to infinity, not including 0. All right, if I want to graph y equals ln of x, then that's my inverse graph. And so I'm just going to switch out my points. I get 1 and 2.7, 0 and 1. So 1, 0, 2.7, 2.7, 1. And so I get this graph, which is symmetric to the line y equals x. And my domain and my range, they just switch out. My domain becomes 0 to infinity, and my range is all real numbers. Because we know the x's become the y's, and the y's become the x's. All right, so now we have some where we're just practicing our rules. So we know that when we are multiplying, we add the exponents. So if I add these exponents, I get e to the 0 power, and anything to the 0 power is 1. When I'm dividing, I subtract exponents, so I get e to the 4 minus e power. And without a calculator, that's about all I can do. For this equation, I have log base e as an exponent. And since those are inverses of one another, I'm just going to get 3x. Now I'm going to go into a little more detail on that one if that's not making sense to you. I'm going to do e to the ln of 3x power equals y. And we're going to rearrange it to log form. So it will be log base e of y equals my exponent ln of 3x. And that we learned, back in Algebra 2 and Pre-Cal, how to rearrange from log to exponent form, exponent to log form. And so I know that ln is log base e. So we can just cross out the logarithms and y equals 3x. So as long as these are the same, and these are inverse functions, exponential and logarithms are inverses, then this 3x, that's always going to be our solution. So with that in mind, we have here another one of those, base e, so my answer here is just 2. You could do the same thing and work it out as well. All right, for the next one, I think I'm going to separate the t over 5 from the element. I'm going to have e the t over 5 power times ln of 2. And we know that we can bring anything that is here in front over as an exponent. So this would equal e to the ln of 2 to the t fifth power. And once I get it into that, I know that these are both base e again, and so my answer would just be 2 to the t fifth power. So that's using some of my rules. I did separate this out so that I could bring it over as an exponent. But once I bring it over, and these are both base e, I'm just going to get 2/5. It's the same principle as number 3 up here. All right, number 6, same rule there. Base e, I just get x squared. Now, all of those, 3, 4, 5, and 6, you could work them out just like I did number 3. But hopefully we can learn the shortcut because there are other things that are going to take our time. All right. So starting with 7, we have some logarithm problems. So again, we're just going to rearrange. This is base e. So back to exponent form, this would be e squared equals 1 over x. And if I'm solving for x, I can multiply both sides by x. and this is gone, and so I have x equals 1 divided by e squared. All right. For number 8, we learned that when we were solving equations, if we can't rearrange and solve, then we could take the log of both sides. In this case, take the natural log of both sides. So the natural log of e to the 2x equals the natural log of 9. The 2x can come to the front. 2x ln of e equals ln of 9. But we know that ln of e is just 1. So we divide by 2. X equals ln of 9 over 2. All right, so all of those are great, helpful things, but what we're going to need for our derivatives, which we're going to be doing in our next lesson, is to be able to expand our logarithms. So probably the most important part of this lesson are going to be these examples here. So if we want to expand these, remember, multiplication can actually become addition. So we would have ln of m squared plus ln of n cubed. And further, we could bring these exponents to the front. So 2 ln of m plus 3 ln of n. All right. Also, number 10 here, the square root is the 1/2 power. So we could replace this with the 1/2 power. And so we have ln of m to the 1/2 over n to the 5/2. Both of those things are raised to the 1/2 power. And then we can separate those. Division becomes subtraction. So ln of m to the 1/2 power minus ln of n to the 5/2 power. And then we can bring the exponents to the front. 1/2 ln of m minus 5/2 ln of n. And that's going to be very important. 9 and 10, very important to what we're going to be doing with our derivatives. Numbers 11 and 12 are just putting our logarithms back together. So we know that as long as these log bases are the same, addition, we can change to multiplication. So we're going to have ln of, also bring over the exponents. So we have ln of p times q to the 3rd power. All right. Also on number 12, we can bring over those exponents, and subtraction becomes division. So we end up with ln of p to the 4th over q to the 2nd. Now, be sure you recognize that whenever we rewrite this as multiplication or division, it's one single logarithm, just like this was one single logarithm separated into separate logarithms. All right, so hopefully this will give you a little review of our exponent and log rules, and we're going to practice before we start taking derivatives.